All right, so Newton's first and second laws of motion. Some things that we kind of already know, and obviously, if you have the paper in front of you, there's some background there. We could talk about videos perhaps that we watch, and we will actually go back and watch these videos afterwards. If you're in Brightspace, then the video is already posted, but in class we're going to watch it sort of like together after. In Newton's first law, we talk about objects in motion. How does that finish? Yeah?
Objects in motion tend to stay in motion unless a force is acted upon them.
Wow. Objects in motion tend to stay in motion unless a force is acted upon them. You know, like with a little bit of modification. Objects in motion will stay in a constant state of motion or a constant velocity unless a net unbalanced force acts upon them. Which is like pretty much the same thing, and I feel like we've been brainwashed since what? Like, what grade did you first hear that in? In chemistry?
No, in your class last year.
Oh, really? Grade 11?
When would I have heard that before?
Oh, I don't know. My daughter heard it in like grade 7, so I thought maybe other people heard it in grade 7. I don't know. But she didn't hear it from me. She heard it from this guy that was teaching her grade 7 teacher, I suppose. All right, well, anyway, that seems like a reasonable thing to say. Objects in motion. Let's put it in writing. Objects in motion. And this isn't like Newton's original Latin or anything, right? Because I don't speak Latin. But objects in motion will tend to continue at a constant velocity and I'm going to tack this in, since we're kind of saying Newton's first law in street language anyway, which includes zero. And you can just imagine somebody raising their finger and waggling it at you while they throw in this little apposition clause. Unless acted upon by a net unbalanced force. And that is a concept-dense sentence, but hopefully it makes sense to everybody. Now, he gets the credit for this, Mr. Newton gets the credit for this, but if you are looking in your book, there are other people that had the same idea. So like in the years between 980 and 1037, there's this other fellow that had basically the Newton's first law idea, talking about objects having an inclination to move in a way that's described as basically the same as Newton. It's not like he invented the idea, but he codified it like in nice language, and he happened to codify it around the time of the scientific revolution in Europe, which is why he gets all the credit, right? So he also codified calculus in around the same time window. So I mean, like, we give credit to this fellow, not because he necessarily was the first one to think the thoughts, but because he wrote it down and people studied the way he wrote it down. Anyway, some examples of Newton's first law. What would be one? Somebody help a fella out. What's an object that would do this? Yep.
Like inertia, like when you are like driving in a car and it comes to a sudden stop, like it's that like jolt you feel. Like,
Yeah.
You move forward until the seatbelt like tightens.
All right. So a rider tending to keep moving. When car stops. What would be another one? Anybody gone bowling? There's actually two examples in bowling. The bowling ball and the pins. Doesn't the ball just keep on rolling until it hits the end of the alley? And the pins just keep on sitting there until a force acts upon them, right? So, I mean, I'm not going to write that whole sentence, but I'm going to say bowling balls and pins. You know, of course, people say, oh, well, what about billiards and pool tables? Yeah, of course, totally, absolutely, that too, right? Anyway, yeah, I always thought this was a neat little thought experiment. So I'm going to zoom in on it, and I want you to give it a read. It's one that I stole from my favorite physics textbook. But give it a second to read this one. I don't want to read it at you. Well, maybe I will. The astronaut in space finds it just as difficult to shake the weightless iron anvil as it would be on Earth. If the anvil is more massive, than the astronaut should be than, there's a typo, than the astronaut, which would shake more? What do you think? Imagine, so this is definitely a thought experiment. There's an astronaut in space. We say weightless in quotes because obviously it's in free fall in orbit around the Earth. But they shake an anvil. I mean, this is very like Bugs Bunny cartoon kind of situation, but you're in space. Why did you take an anvil there? Who cares? That's a side issue, okay? But you're in space and you have an anvil and you shake it. It's hard. It's hard to move the anvil. What's the property that the anvil has that makes it hard? I'll give you a hint. It starts with an I. Lillian? Lillian's shaking it off. The property that an object has that makes it hard to shake it or move it starts with an I. Yeah? Inertia, yeah. Inertia. And inertia is the name that we give to that tendency. Inertia is the name that we give to that tendency to keep on doing what it's doing. Whether it's moving at a constant velocity that's not zero or remaining at a velocity that is zero, it's going to keep on doing what it's doing because of inertia. And inertia is closely connected to mass. The more mass you got, the more inertia you got. So I think that kind of ties into the second half of this question. The second half of this question is, if the anvil was more massive than the person, which would shake more? The astronaut or the anvil? The astronaut, right? It would be like the anvil shaking the astronaut. And you can imagine this, you scale this thing up, if this was a whole space station, and if you tried to shake the space station, wouldn't you be the one that's getting shook? It makes sense. There's a mass imbalance. The space station would have way more inertia, way more tendency to stay put. And it's weird to think, because we think, weightlessness. It would be so easy to move masses around in space. And while there's not like this overwhelming force due to gravity that would make it hard for us to lift these things, they still have a tendency to stay put. They tend to stay in their state of motion, Newton might have said, you know? And I think before I saw this little blurb out of a textbook, I fully stole it. But before I saw this, I hadn't really thought about it. I really had not thought about shaking anvils in space and how the absence of gravity wasn't going to remove the idea of inertia. And I think that's kind of a big deal. To recognize that inertia and weight and mass are all different things, but obviously there's crossovers, there's connections, okay? So I think that little thought experiment, at least for me, crystallized that idea in my mind. I don't know if it's good for you or not. All right, I want to keep on going though, because this is the idea of Newton's first law. We've got a street language definition. We've got the idea of what inertia is, and maybe a weird scenario that fits more like in a comic book kind of world than in the real world, but it still definitely is a thing, right? And then we got Newton's second law. So Newton's second law, we could say it in sentence form. And basically, very few people actually say it in sentence form. But if we were going to say it in sentence form, we'd say the acceleration of an object is directly proportional to the force applied to it. In other words, F is directly proportional to A. The more you F something, the more it'll A. Right? That's what direct proportionality means. And if I was going to graph such a proportionality, it might look something like this. Look at that. The more I F it, the more it A's. That makes sense. Yes. The acceleration of an object is inversely proportional to the mass of an object being pushed. Now, the way we write that in a proportionality statement is A proportional to 1 over M. Let's talk about, again, what that means. The bigger the M, isn't it harder to A that thing? Yeah, I think so. Look, if I'm trying to accelerate something, it makes sense that if I have a little tiny m, I can achieve a really big A. But if I have a really big M, I'm only going to be able to achieve a little tiny A, because it's going to take what? More force or less force to A that big M? Come on. More force, right? Take less force to A that little m. And so if we whack these two guys together, these two proportionality statements together, we actually get this nice math statement. We could write it as, based on these two proportionalities, we could write it as A is equal to F over M, where, look, the bigger the M, the smaller the A, the smaller the M, the bigger the A for a constant F. Or we could say, hey, more F on a constant M is going to mean more A, which is what the first statement says. And people typically don't leave it in this format. They typically will rewrite it as F equals MA, even though the first way of writing it kind of fits better with the sentence definition, you know? And people just like to clear the denominator. I think that's kind of a common way of writing things, probably because it's easier to type, you know, like keep it all in the same row. But I mean, F equals MA is a nice way to write everything. Newton himself didn't really conceptualize it this way. From things that I've read, Newton talked about it not being F equals MA, but hey, you know what? Maybe I'll just do like a quick little aside at the top of the page. In terms of Newton thinking, F equals MA, we've talked about in kinematics, A being the change in velocity, v2 minus v1, divided by the amount of time that goes by. And so we could expand that acceleration out to delta v over delta t, essentially. But if I use the distributive property, don't tell anybody that I have two equal signs on the same line. My math teacher friend will hurt me. But you end up getting mv2 minus mv1 over delta t. And previously, we talked really briefly about momentum. Momentum is mass times velocity. Momentum, notice, mass times velocity is a calculated value. And if you we're talking about like street language and expressing physics idea the way the common person experiences or talks about them, mass times velocity is momentum, but inertia is not mass times velocity. But if you talk to somebody, you know, like everyday language, oh, how'd the hockey game go? Oh, well, you know, like, we really had a lot of momentum going into the finals, eh? But we didn't have the inertia to carry us through to the next round. And, you know, like coach just says, we got to try harder next time, dig deep, lean in. And you just throw those two words out there, inertia, momentum, and it sounds like they mean the same thing. Inertia is the tendency of a mass to continue doing what it's doing. Notice tendency, not a calculated value. Mass times velocity is momentum. They're both connected to mass, but they're definitely distinctly different things, okay? Anyway, what Newton would have said is that momentum is the rate of change. Force is the rate of change of momentum. Notice that this is a momentum final minus momentum initial, if you like. And actually, people use the letter P for momentum. I'll tell you why later. Oh, maybe I don't even have to tell you why later. I'll tell you why now, but just give me a second. He would have written it as P2 minus P1 divided by delta T. And the reason he used P for momentum is because mass was already taken. Like M was already taken by mass. And in Latin, he used the word impetus for momentum. And I had already been taken by another variable. So he just moved on to the third letter, P. It almost seems like this random, silly reason to choose P for momentum. I and M were taken already. That's it. And if you read something different, let me know, because that's what I've read about it, because I was really curious about this one, you know? Weird. All right, anyway, all the way down here, we say F equals ma. Newton might have said rate of change of momentum over time. And for now, at least, we're going to stick with the F equals ma way of thinking about it. But I just wanted to make sure that we all kind of have this idea in our heads that, you know, maybe Newton is really consistent about his thinking. He's really into rates of change, right? You notice that, like a big theme in calculus. And so even the second law is actually thought of by him as a rate of change. Anyway, so I've got this object. So I want to deal with this as a free body diagram. And if I'm going to do that, I'm going to define a reference frame. And I think that at least for these two free body diagrams, let's just agree to have the same free body diagram reference frame, north, south, east, west. We'll make north be positive and east be positive and south and west be negative. And it says that we got to find the acceleration. Well, this is the easiest one of all. And you guys can probably beat me to this. I would say F net is equal to mass times the acceleration. I could say the acceleration of the system, but it's a one-body system, so that's maybe a little extra. If I really wanted to put a arrow hat over top of my vectors, I definitely could be good about that. But anyway, if I wanted to accelerate for the acceleration of this system, it would just be F net over m. And F1 is the only force here, so it's 10.0 newtons divided by a mass of 5.0, looks like kilograms. And just as a quick aside, and to make sure that everybody remembers, a newton, even though it is this fellow's last name, is really just a shorthand way of writing kilogram meters per second squared. And so when I have newtons divided by kilograms, I'm going to cancel out the kilograms and leave behind meters per second squared. And 10 divided by 5, of course, is 2. And there's only two significant figures there. So I'm going to say 2.0 meters per second squared. Now, for lack of space, since this answer is positive, and since the acceleration gets its directionality from the net force, if the net force was towards the east, then the acceleration is going to be east, yeah. So I kind of did two steps in one there. I rounded to 2 sig figs, and I applied the positive answer as east. Just really to save space. I want to break up the workspace here. Now I got a situation where, somebody could argue this is like a tug of war. And if it's a tug of war, that means that the net force expression, maybe later on, could be written as force 1 plus force 2. It's only a one-dimensional tug of war, it's back and forth. But what that means is that when I get my acceleration of the system statement set up, I'll just jump to that step. A sys is equal to F net divided by m. And I could write mass of the system if I really wanted to go crazy with the subscripts here, but it's a one-body system. So I'm just going to write m. Anyway, F net would be force 1 plus force 2. And I'm going to treat the labels on this diagram as my list of givens, just for simplicity. But when I go to sub in my values, notice that force 1, based on the reference frame that we agreed upon before, is a positive value. So force 1 is 10.0 newtons. And force 2, I can add on negative 12.0 newtons divided by the mass. Same mass, 5.0 kilograms. And I end up getting 10 minus 12, negative 2. Negative 2 divided by 5. In your head, what is it? 2 over 5? Starts with a 4? Starts with a 0? 0.4? Yeah? Okay. So 0.4 is 0, and it's meters per second squared for the same unit canceling reasons as before. But is it positive or negative? It can be negative. So be careful. So that negative means that it was to the west, so 0.40 meters per second squared to the west. And you always want to apply the directionality. If you're somebody who stylistically likes to put your negative signs in when you sub in your values, the way that I just did it is great. If stylistically you like to deal with the fact that force 2 is in the negative direction when you construct your formula, then you would have written it as equals F1 minus F2 divided by m. But then when you sub it in, you'd sub them both in as positive values because you can't deal with the negative sign twice, right? You would have dealt with the negative sign at this stage for the force 1 or force 2 rather than at this stage. So just be careful that you don't use the negative sign 2 times. I've seen a few people do that one. Anyway, I'd say 10.0 newtons minus 12.0 newtons divided by 5.0 kilograms. And you end up getting to the same thing anyway. It's just a question of when we insert the negative sign, whether it's at the formula level or if it's at the data subbed in level. But it can't be both, is all I'm saying. Let's take a look at the next page.